here, as you can see, we have two alternatives. When I finished the theoretical part, I will show you on Minitab, like I said 5 minutes ago. We didn't finish the theoretical part yet. Once it's finished, I will show you in Minitab, inshallah. How question in CPHQ? I am not specialized in CPHQ, and this lecture has no relation with CPHQ. Maybe have some relations with Six Sigma, but it has no relation with CPHQ. CPHQ don't have any large statistics amount. So excuse me, but this is not relation with the CPHQ. Can we compare more than 2 sets of data? Yes. Yes, you can compare sample to target, 2 samples to each others, and 3 or more samples if you wish, Abdelhamid. Yes, you can. And each one have its own test. I will show you the roadmaps after a while, inshallah. For example, we have a test called ANOVA. If the 3 samples or more you are comparing are continuous and normally distributed after test of normality, then we can use test called ANOVA, analysis of variance, to compare between 3 means or more. So as it was apparent intuitively, you have 2 alternatives or 2 scenarios or 2 options. The null hypothesis, H note, which assumes that there is no difference or relationship. And this is the default assumption. This is something like the law or like the juries, which means that any convinced person is innocent until we have enough evidence to judge him. This is a very famous rule in Arabic. المتهم بريء حتى تثبت إدانته. Every candidate or every prisoner is innocent until we have enough evidence to judge him. It is the same idea here. So the H note, which always have an equal sign, will always assume that you did nothing. 2 suppliers like each other, 3 waiting times for different clinics are like each other, no relationship, and so on. But on the other hand, the alternative hypothesis will state the opposite, that there is difference or relationship or so on. And the p-value will guide us whether to accept the null hypothesis or to accept the alternative hypothesis. And actually in statistics, we do not pronounce it like this. We don't accept anything. It will seem intimidating, but it's okay. I will not focus much on it in this free course. If the p-value is greater than or equal to 0.5, I will not say that I will take the null hypothesis. No, I will say statistically, fail to reject the null. Fail to reject the null. I don't have enough evidence to reject the null, so I will take it or accept it. But we never say in statistics accept the null or take the null. Fail to reject. Nafi is bad for Arabic speakers. On the other hand, if I get a p-value which is less than 0.05, I will never say take the alternative hypothesis or accept the alternative. No, I will say reject the null. Reject the null. When you reject the null, you're left with the alternative hypothesis. And if any one of you do some statistical analysis for his master or PhD on a certain office or certain agency, or even read some research papers and focus on the statistical analysis of it, you can clearly see that it's well written like this: either fail to reject the null or reject the null. We'll never say in statistics accept the null or accept the alternative hypothesis, but it is not an issue right now. Our objective from this free course is to just to give you a deeper idea about the advanced tool in statistics. Okay, next. So you can say that our roadmap or our steps to a statistical hypothesis test, that we state the practical problem. Practical problem, everyone can understand it in our organization. Practical problem, it means we have 2 suppliers and we need to take decision whether to rely on supplier 1 or supplier 2. Or we have a certain KPI and you need to detect statistically whether we achieve the target or not. This is very easy and anyone can understand it. Step number 2, you will convert the practical problem into statistical problem, writing your H note and HA like I'm doing in the last 30 minutes. Then you have to set alpha and beta, and already alpha and beta in any statistical software already set for you. Alpha is 5%, okay, which is type 1 error, or the 5% remaining from 95% confidence level. And we, in a minute, we'll speak about what is beta error. Ignore it for the now being. Then you start your test, getting a p-value. The p-value will give you some statistical solution. Then you have to convert this into a practical solution, because people will not understand what you are saying. Reject the null and they fail to reject the null. This is a statistical solution. You have to give them practical solution they can understand. No difference. Supplier 1 is better than supplier 2. We hit the target, we don't hit the target, and so on. So this is very important to convert again the statistical solution into a practical solution. This slide is very important, or part of it is very important to understand what is the p-value actually represents. We talked about p alone without value. P is a probability, 0 or 1, blah, 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 blah. Okay, so what is the p-value by any? So any differences you can see practically, which is a practical significance, between your observed data and the claims you made may be real or may be due to chance. And the statistical significance will solve this problem for you, will tell you whether there is difference or not, you hit the target or not, whether this is due to chance or not. So what is the p-value by any? Hypotheses determine the probabilities of these differences occurring solely due to chance. In Arabic, احتمال الصدفة. So the p-value is the probability of a chance. That's why if we go here, when the probability of a chance is high, more than or equal to 0.05, I told you to take the null hypothesis, which is the same. We have the same, no difference relationship, and so on. Because likely the variation or the change we are observing is solely due to chance. On the other hand, when the p-value, which is the probability of a chance, is less than 0.05, it means it's very low, then I told you to pick the alternative hypothesis, which means that really there is significance, there is a relationship, there is a difference, and so on. So simply, the most simplest definition for the p-value is it is a probability of a chance. Probability that the change or the relationship or the difference I'm observing is solely due to chance, due to random sampling error I talked about last Friday. So when this probability again is very high, we'll go H naught. When it's very low, less than 0.05, I will go with the HA. Okay. The most commonly used levels of alpha, we agreed that 5% is the most widespread value, and this will give us 95% confidence level. But in some circumstances, with fair justification, we can set alpha to be 10%. It means that the confidence level now is 90%. And also we can set to only 1%, and that will set confidence level to 99%. And one of you can wonder, please, sir, if I can set alpha to 1% and get a confidence level of 99%, so why you are bothering us with your 5%? I will tell you in the next sections, inshallah. But changing the confidence level and the alpha usually must be done by a statistician, and it also must have a great and fair justification why you are changing this. Because everything has a pros and cons, and I will tell you what are the cons of this case, because for the first while it seems perfect. The alpha is 1% lower, much lower than 5%, and my confidence interval is much higher than 95%. So everything is good. Why you are sticking to 95 and 5? I will explain this in the minutes, specifically when we understand difference between alpha and beta, type 1 error and type 2 error. I will not go through the materials here because this is a black belt materials. Don't have time to explain everything. I just want to shed light on alpha and beta. So the alpha risk, and it's called risk, or sometimes called type 1 error, which is, as we said before, is 5%. It is the probability of rejecting a null when the null is true. The probability from 0 to 1 to reject a null. Reject a null, it means you picked HA. While the null is true, you shouldn't do this. On the other hand, the beta error is the probability of accepting a null while the null is false. So if I continue here to the beta error, again, beta error, the probability of accepting null, so you say no difference or no relation or whatever, while there is a relationship. That's what meant here in material probability. We could be wrong in saying two or more things are the same when in fact they are different. Probability of accepting a null, no difference, while the null is false. And you must understand that alpha and beta usually we set it to, by the way, 10%. So this is alpha, and this is beta. You must understand the physical meaning of alpha and beta. The risk of alpha and beta are really true. How? For example, if you are in the, like our example, if you are comparing supplier 1 to supplier 2. For sure, in your practical life, you will do this comparison once, only one time. If you repeat this comparison, or if you make 100 hypothesis tests in row, there is a probability that 5 times from these 100 times, the p-value will tell you that you have to reject a null, while actually this is untrue. You have to accept a null. So this is real. It's not fancy thing. On the other hand, beta, 10%. 10%, it means if you repeat it again 100 times in row, there is 10 times out of 100 times in which the p-value, which will come from any statistical package, or even manually if you are a statistician, will tell you to accept the null, which means no difference, while actually there are really different. So alpha and beta risk are real, and this is the cost we are paying because we don't have thing better than 95% confidence level. And for sure, this will be apparent when you repeat your hypothesis testing 100 times. But actually, this will not be the case practically. In practice, you do it only once. So the probability that you fall within one of them is very low. And this is the cost, again, we pay when we say that the confidence interval is 95% and the alpha is 5%. So alpha is real. That's why it's called alpha risk or beta risk, because it is a risk you are taking. Because maybe this one out of 100, maybe you will be fall within this error or not. But the good news is that the p-value you are getting from any practical software is already considering the alpha and beta. So you don't have to modify the p-value or to do something behind the p-value. The p-value already taking into consideration alpha 5% and beta 10%. And this is what was written here in the steps. If I get here. alpha 5%, beta 10%. This is fixed in the settings of Minitab and SPSS and. So all to sum up, all what you have to do is to just translate or interpret the p-value you get based on the criteria we set. If p is high, null is the guy. If p is low, the null will go, and you are done. Thank you very much. But theoretically, you, as someone who are using statistical package or using statistics, you have to understand what is alpha and what is beta, and their risk is really something may happen. It is not a fancy thing. Okay, so what else? The last thing here in alpha and beta is my answer to any one of you wondering why I did not decrease the alpha to 1% and I have a confidence level of 99% and all set. I'm fine. Unfortunately, there is an inverse relationship between alpha and beta. There is an inverse relationship between alpha and beta. So in summary, what is the reason of 95% confidence level is better than 99 confidence? This is exactly what I'm about to say. So if you just bear with me for minutes, you will know. It is not better. It is not about which is better and which is bad. I'm justifying why 95% is the most widespread. There is an inverse relationship between alpha and beta. So when you increase alpha, so you decrease alpha from 5 to 1%, to decrease your confidence level to 99%, the beta error will increase. It will be, for example, 15%. And this is something not accepted by any statistician. Likewise, if you decide to decrease beta to be, for example, only 5%, alpha also will increase to be 10%. So nothing is better than nothing. If it was better, I couldn't say that you can under justification. You have to justify. If you convinced a statistician or statistician convinced you why you have to change alpha and beta, we can start to talk. But in business, in management, in Six Sigma, in quality, in any applied statistical industry, we will preserve 5% and 10%. Why? Because if you decreased alpha from 5 to 1, yes, this will increase your confidence level, but on the other hand, it will increase the beta error. And from our bootstrapping and simulation studies, because a lot of simulation is used in statistics when we try to prove something, we are trying to simulating population and do another more than one experiment on it. We found that keeping alpha at 5% and keeping beta at 10% is the best combination. That's why 95% is widely used than any other value of alpha. I hope that this will answer your question. And also there is another thing, which is away than alpha and beta. If you increased the confidence level to be 99% by decreasing alpha from 5 to 1%, this will increase the confidence level, but on the cost of the width of the confidence intervals. The degree of uncertainty here will be larger or wider. But if I keep it 95%, it will give me much narrower confidence interval. What do you mean by wider and narrower? It is not about the sketch or diagram or font, no. When you increase the confidence level to be 99%, as I said here, this is have a cost. Nothing in statistics come without cost. The cost is that the degree of uncertainty in the location of the population mean, for example, will increase. It means if I keep it 95%, I will say the population mean lies between 10 and 12. If the same sample, I use 99%, I tell you I can't be confident enough. So I will say from 8 to 13, for example. Can you realize the difference? Everything has a cost. If 99% is better, so it is not widely used worldwide. Everything has a reason, everything has a cost. So when you increase the confidence level to 99%, not only the beta error will increase to be 15 or 20%. This is not accepted because we found that 5 and 10 are the best using our simulation studies. And you can find the proof in any statistical text. I give you another more practical clue. When you're increasing the confidence interval, the degree of uncertainty in your confidence level will increase as well. So I can't locate the population mean precisely like 95. I will give you wider confidence interval from 8 to 13 or 8 to 14. But if I keep it 95%, this width will increase. I can give you narrower confidence interval. I can be sure now that the population mean only between 10 and 12. This is for the question which may pop up in the mind of any one of you, why we just don't use confidence level of 99% and keep alpha and 1% and voila.